to the fourth and final of our July lectures in physics for 2011, continuing our celebration of the 100th anniversary of the discovery of superconductivity. My name is Professor David Jamieson, and I'm the head of the School of Physics and the organiser of the July lecture program. It's my enormous pleasure tonight to introduce my colleague, Associate Professor Andrew Melatos. Andrew is one of Australia's most distinguished theorists in the topic of tonight's lecture. Andrew is a member of the international consortium that runs the Large Gravity Wave Detector Laboratories in the United States, the LIGO facility. He has very strong connections with the leaders in the field, including those at the Albert Einstein Institute in Germany. Andrew has diverse interests in the topic of tonight's lecture, where he conducts research in collaboration with his international colleagues and a large cohort of PhD students here at the University of Melbourne. Andrew comes to us with a PhD from the University of Sydney, where he also won the University Medal, and he today conducts his programs with the support from a grant that he has won from the Australian Research Council that funds the most elite and best research in Australia. He also, though, is not just an accomplished physicist. Andrew has diverse interests in applying principles of physics to sociological problems, including finance. He also maintains a deep interest in the culture of physics and its origins in deep antiquity. He is capable of discussing at depth any aspect of physics and always is an excellent luncheon companion. And I should say also that he is one of our most accomplished lecturers in the undergraduate program, where not only is he renowned for the clarity of his lectures, but also the passion with which he delivers the material. So it's my enormous pleasure to invite Andrew to the stage tonight.
I may deliver the lectures passionately, but I can't get the screen to work. Okay, well, thank you, David, and thank you all very, very much for coming to this last lecture in the July lecture series. It's not often, I must admit, that I have the opportunity to speak uninterrupted to such a large group of people about my research for, would you say, 2.5 hours? Just kidding. But yes, look, it's really lovely to see you all here, and I hope you enjoy today's topic, which is the question, which touches on this question of superconductivity in space, and in particular, superconductivity in a certain kind of cosmic object known as a neutron star. I might just allow to get these sorted. That was my fault for putting that. Yes, so the outline of the talk, just briefly, is that first I'll tell you, for those of you who aren't familiar with them, what neutron stars are and why we find them very interesting. Then I'll talk about a little bit the bizarre quantum mechanics that happens when you take huge amounts of matter, like in a neutron star, pack them together, freeze them, make the matter very cold, and then look at what happens. And it turns out that quantum mechanics goes a little bit crazy under those conditions, and you get very, very interesting phenomena, the phenomena of superfluidity, and its very close cousin, the phenomenon of superconductivity. And what we'll find is that there are effects, phenomena in neutron stars, which essentially reflect these two underlying physical processes. David mentioned that we're strongly involved here at Melbourne in the LIGO Virgo consortium, which is hoping to detect Einstein's gravitational waves for the first time in the next 2 or 3 years. It turns out that gravitational waves, when they are detected, will be excellent probes of this very strange quantum physics and excellent windows into the interiors of neutron stars. And so, although gravitational waves won't be the subject of this talk, I'll try to show you how we hope to use them to learn about these things. Okay, our story begins in 1054, July the 4th, shortly before my birthday. Not the year, and what you have here is a quote from the imperial astronomer in China at the time. In the first year of the period, I won't try to pronounce it, a guest star appeared in the sky. To people in China at the time, they looked up that day and they saw in broad daylight, and this was also true of course at night, a new star in the sky, a very bright star, second in brightness only to the sun. And for the next month, that star glowed, day and night, slowly dimming, but visible for all to see. That guest star, oh, by the way, you'll note that the imperial astronomer was politically astute, so he made appropriate comments about the star not disturbing the emperor's favourite part of the sky. That guest star was what we know today as a supernova. The death of a giant star, maybe 10 times the mass of the sun, maybe a bit more, maybe 20 times the mass of the sun, which reaches the end of its life, runs out of nuclear fuel, collapses in upon itself, because when it runs out of fuel there's nothing to hold it up against gravity, implodes, then explodes in a giant explosion, which, as I say, we know today as a supernova. And I remind you, many of you will know this, that for a few minutes, a supernova is brighter than all the other 10 billion stars of the galaxy combined. This one happened about 2,000 light years away, and what you see here is a beautiful image from the Hubble Space Telescope, an optical image, a collage of optical images, that shows the Crab Nebula. This is the debris of the explosion, of the supernova explosion, which occurred somewhere in here from here. This debris, it's not the subject of this talk, but it's just worth remembering that this debris contains the elements that make up planets like the Earth, that make up the next generation of stars, and that make up humans. The uranium atoms and all of the atoms in your body that are heavier than iron have been produced in supernova explosions like these. They get scattered through the galaxy and then incorporated into new generations of stars, and as I say, into planets and ultimately into things like people. So, what is left behind? Well, we've already seen one thing that's left behind, the glowing debris. The other remnant is a neutron star, or a black hole, and I won't be talking about black holes in this talk because the subject is superconductivity, which is irrelevant as far as we know to black holes. This is a picture, an X-ray picture taken by the Chandra telescope of the supernova remnant Cassiopeia A. It looks quite similar in some sort of generic way to the crab, which we saw before. Now, this was a more recent explosion, about 400 years ago. But the difference is that here you can see very clearly a bright point source. And remember, this is an X-ray image. So these are X-rays coming from this very hot object. And that object is the neutron star. Now, what are these neutron stars? Well, they are the ash left over from the supernova explosion, and they, as we will see in a minute, are very dense. So their interiors consist of electrons and protons that have been squashed together to form neutrons, with the release, as that process occurs, of neutrinos. And you may have heard in the previous lectures in this series, perhaps from Professor Volkas, about neutrinos. These are ghostly subatomic particles that, happily travel without scattering through miles and miles and miles of lead, light years actually, of lead, and are produced in copious numbers within neutron stars. They are responsible for cooling the star down, and we'll see in a moment that that's important, that neutron stars are cold. Neutrons are left behind, mostly, although there are some electrons and protons as well. The mass of the object is about 1.4 solar masses. Its radius is 10 kilometres, roughly the size of Melbourne. And what this, of course, means is that it is incredibly dense. So, what we always say, if you go to the surface of a neutron star and pick up a teaspoon of neutron star matter, then that teaspoon weighs about 1 billion tonnes. It's not recommended to go to the surface and dig around with a teaspoon, but that's another matter. Ethics approvals for that experiment forthcoming. Now, inside a neutron star is different to a star like the Sun in the sense that it doesn't contain